This tutorial is brought to you by PE Prep Engine. Free study guides and practice questions at peprepengine.com.
Week 3, Lesson 7, Tension Connections, Preload and Joint Stiffness. Last lesson found the proof load, the largest tension a bolt takes with no permanent set. But a real bolt is never just pulled to failure. It's tightened first to a preload, and then it shares any external load with the clamped members around it. The surprise is how little of that external load the bolt actually feels. This lesson builds the picture. A preloaded joint has two springs in parallel, the stiffness constant that divides the load, and the point where the joint lets go. Here's the problem. A bolted joint with a known bolt stiffness and member stiffness, a preload already set, and an external tensile pull applied. Find three things: the joint stiffness constant and how much of the pull the bolt takes, the resultant bolt load, and ask yourself whether that's just preload plus external load, and finally the separation load, the pull that finally opens the joint. Watch question 2. The intuition that the bolt feels 40 plus 30 is the single most common mistake in bolted joint problems. Concept 1. Two springs in parallel. Tightening the bolt does two things at once. It stretches the bolt in tension and squeezes the clamped members in equal compression. Now apply an external pull. The grip stretches a hair, and both the bolt and the members feel that same tiny deflection. Equal deflection, shared load. That's exactly two springs in parallel. And here's the key. The members are short and stocky, while the bolt is long and slender. So the member stiffness is usually far greater. The stiffer path carries the bigger share, so the members swallow most of the pull, and the bolt gets only a sliver. Concept 2. The bolt sees only C times P. The load splits by stiffness, and the bolt's fraction is the joint stiffness constant C, bolt stiffness, over the sum of the two. The members take the rest, 1 minus C. Because the members are so much stiffer, C is small, commonly between about 1/10 and 1/3. So of the external pull, the bolt picks up only C times P on top of its preload, and the members give up the rest of their clamp. That makes the resultant bolt load the preload plus a small fraction of P, never the full preload plus P. Burn that in. FB is FI plus C times P. Concept 3. Clamp, then separation. The external pull barely stretches the bolt. What it really does is relieve the compression the preload put into the members. The joint stays clamped as long as some of that compression survives. Push the pull higher and the member clamp shrinks towards 0. At the separation load, the clamp hits 0 and the members lift off. After that, the two-spring split is dead. There are no members left to share, so the bolt alone carries the entire external load. A good design keeps the working load safely below separation, so the joint never opens. Setup. Part 1. The Handbook load-sharing equations all on one page. The bolt's share of the external load is P times the joint constant C. The resultant bolt load is that share plus the preload. The resultant member load is the member share minus the preload. And the joint stiffness constant is bolt stiffness over the sum. These are exactly as the handbook prints them, validity tag and all. We'll turn the tag into a practical clamped or separated check, using the separation load in a moment. Setup. Part 2. What the exam actually gives you. Every quantity here is either handed to you or computed from the ones that are. The preload, the external load, and both stiffnesses arrive as given numbers. The joint constant is either computed from them or stated outright. And only the resultant bolt and member loads are things you work out. Crucially, the handbook prints no formula for member stiffness. No grip frustum, no area times modulus over length. So you never derive the stiffnesses from geometry. They are always inputs. Solve. The joint constant and the bolt load. C is bolt stiffness over the sum, which comes out to 0.2. So the bolt's share of the external pull is C times P, just 6 of the 30. Add that to the preload and the resultant bolt load is 46. Compare that to the naive preload plus full load answer of 70. The real bolt load is more than 50% lower, because the stiff members quietly absorbed most of the pull. That gap is exactly why preloaded joints shrug off fluctuating loads. Solve. the clamp check, and separation load. Plug into the Handbook's member equation, and the resultant member load comes out negative, which simply means the members are still in net compression, with 16 kilonewtons of clamp left, so the joint is seated. Separation is where that clamp runs out. Set the member's share of the external load equal to the preload, and the separation load is preload over 1 minus C, 50. This one is derived, not printed, so it carries no citation. Our working pull is 30, comfortably below 50, which matches the 16 kilonewtons of clamp we still have. The joint holds with room to spare. Traps. 5 ways this bites. 1. The bolt does not see preload plus the full external load. It sees preload plus C times P, because the members swallow the rest. That's the single biggest bolted joint error. 2. Don't flip C. Bolt stiffness goes on top, and stiff members make C small. 3. The load split dies at separation. Above the separation load, the bolt carries everything. 4. Don't derive the stiffnesses from geometry. The handbook gives them, or gives C. 5. A negative member load just means clamp remains. Judge seated versus separated by comparing the pull to the separation load. Quick recall. The joint constant is bolt stiffness over the sum. The bolt's share of an external pull is C times P, so the resultant bolt load is preload plus C times P, not preload plus the whole load. The members shed 1 minus C of the pull, and the joint separates when the pull reaches preload over 1 minus C. The stiffnesses are always given, never derived from geometry. Remember the worked joint. A stiffness constant of 1/5 gave a bolt load of 46, not 70, and a separation load of 50. The stiff members shield the bolt, as long as the joint stays clamped. Next up, Lesson 8, Bolt Torque Requirements. Here we treated the preload as a given number, but in the field you can't set preload directly. You get to it by tightening the bolt to a target torque. Lesson 8 closes that loop, how tightening torque relates to preload through thread and head friction, and how the preload itself is pegged to the proof load you found back in Lesson 6. Preload in, torque out. Everything's at pprepengine.com. Cheat sheet, work solution, and a quiz attached here.
The full study guide, with every equation and common exam trap, is free at pprepengine.com. Link in the description. Machine design, HVAC, structural, civil, and electrical series are coming soon. Subscribe so you don't miss them.